Uh, Welcome to our seminar. Today we are very happy to have Maurice from MIT, and he will tell us about integrability in Liouville quantum gravity. Thanks, Maurice.
Thanks very much for the kind invitation to speak here. This talk is based on a program with Sun on integrability in random conformal geometry. And I'll be speaking on works that are joined with Nina Holden and Guillaume Remy and Sun. Yeah. Okay, so Liouville quantum gravity, or LQG for short, was proposed by Polyakov in the 1980s as a canonical model of random surfaces. And more recently, in the last decade or so, mathematicians have been proving theorems on this as well. And two main directions of research are as follows. So the first approach is the random planar geometry approach, which is inspired by the interpretation of LQG as a scaling limit of random planar maps. In this approach, there are natural couplings with random planar curves called Schramm-Loewner evolution. These curves arise as interfaces when random surfaces are glued together along their boundaries, or when a random surface is constructed as a mating of trees. Okay, the second approach focuses on the conformal field theory that underlies LQG, called Liouville conformal field theory, or LCFT. So the probabilistic construction of LCFT makes rigorous the path integral formalism set out by Polyakov. LCFT exhibits a very rich structure that arises from its conformal symmetries, and consequently, we can prove many of its correlation functions. We can explicitly compute these correlation functions. So in this talk, I want to explore connections between these two approaches and consequently prove new formulas in each direction. Okay, so I'm first going to discuss these two approaches in more detail, and the remaining three sections of the talk will be on original research. Okay, so the Gaussian free field, or GFF for short, is a random generalized function on the unit disk that we can construct as follows. So let H be the space of smooth functions on the closed unit disk, which have mean zero on the boundary of the disk. And we equip the space with the Dirichlet inner product, which is given here. This is the L2 product of the derivative. So let Fn be an orthonormal basis in the closure of this Hilbert space. And to sample the Gaussian free field H, we first sample a sequence of independent Gaussians alpha n, which are normal with variance 1. And then we set H equal to the sum of alpha n Fn. So the law of H does not depend on the choice of orthonormal basis. H is not a function, we cannot evaluate it pointwise, but it is a generalized function. So we can make sense of it by testing against smooth functions, say. Okay. So now we explain the LQG geometry associated to the Gaussian free field. We fix a parameter gamma between 0 and 2. And this is the LQG parameter. And for most of this talk, this will be implicit. Now for a point Z in the closed unit disk, consider the circle of radius epsilon around Z, and let H sub epsilon of Z be the average of H on this circle. And if the circle is not contained in the unit disk, like if Z is a point on the boundary, then we just take the segment of the circle that is in the disk. Okay. So now we can define the gamma LQG area, or quantum area. Formally speaking, this is a measure on the unit disk given by e to the gamma hz d squared z. And this doesn't make rigorous sense because we cannot evaluate h pointwise, but instead, we can use a regularization and renormalization approach where we replace h of c with h epsilon of c. Yeah. And in a similar fashion, we can construct the gamma LQG boundary length or quantum boundary length using regularization and renormalization. Okay, so the point is that given the Gaussian free field H, we can define a random area measure on the unit disk called A sub H, and a random measure on the boundary of the unit disk called L sub H. So these are instances of what is called Gaussian multiplicative chaos. Okay. For continuous functions G on the closed unit disk, we can also make sense of the quantum area and boundary length associated to the field H plus G. And finally, we know that in a remarkable collection of works that were recently done, the LQG metric was constructed. And for this talk, this is not something that I'm going to get into. Okay, great. Now we can define the Liouville field on the unit disk. So we call the LQG parameter gamma between 0 and 2, and let Q be equal to gamma over 2 plus 2 over gamma. We also write P sub D for the law of the Gaussian free field on the unit disk. So to sample the Liouville field on the disk, we first sample a Gaussian free field H from P sub D, and then we independently sample a real number C from this infinite measure here, given by e to the minus QC dC. So this gives us a random pair, H comma C. We write phi equal to H plus C and call phi the Liouville field. We also say that LFD is the law of phi. So LFD is an infinite measure on the space of distributions. Okay, so let me briefly discuss why this plus C term here makes sense. So when we defined the Gaussian free field, it was normalized to have average 0 on the unit circle. And this is a kind of arbitrary choice. And so adding this random constant C removes the arbitrariness of the GFF normalization. So this kind of makes sense. Okay, so a quick remark on notation. So in this talk, I'll often be speaking of non-probability measures, but it's still convenient to use the vocabulary of probability theory. So for instance, I said sample C from this infinite measure. And I also said LF sub D is the law of phi, even though LFD is not a probability measure. I hope this is not confusing. Okay, great. So the Liouville field that we have just defined is a rigorous way of making sense of the path integral formalism of LCFT. In his seminal work in 1981, Polyakov defines the Liouville CFT via this integral here, where S sub L is a Liouville action, and d phi is the formal Lebesgue measure on the space of all functions from the unit disk to the real line. So this doesn't make sense vigorously, but the Liouville field that we defined in the previous slide can be considered as a rigorous interpretation of this integral. So okay. So we sample a field phi from LFD, and we weight by the exponential of the quantum area and the quantum boundary length times these constants mu and mu b, and we evaluate against a test function. And so this describes a measure on the space of distributions. Okay, so this has been done on the disk, sphere, and other topologies. Let me highlight a special choice of F, which is of great importance in the physics literature. So we want to take F to be the exponential of the function phi evaluated at several points, some possibly in the bulk or on the boundary of the unit disk. So again, this does not make rigorous sense. So we cannot just plug it into this integral here. So we have to make sense of the Liouville field with insertions. So suppose alpha is a real number and z is a point in the unit disk, and beta is a real number and x is a point on the unit circle. Then we can define the Liouville field with insertions by first sampling a Liouville field without insertions, and then weighting by this function f, which is e to the alpha I phi of zi times e to the j over 2 phi of xj. And again, this doesn't make sense rigorously, but we just take a certain regularization and renormalization and send epsilon to 0. And then this does give us a rigorous construction. So what does a Liouville field look like? Well, when we're close to an insertion in the bulk, say alpha comma z, the field looks like a Gaussian free field plus an alpha log singularity around z. And the same comment can be made for boundary insertions, beta comma x. Okay. So given this construction of the Liouville field with insertions, we can now make sense of the special case where f was equal to that exponential, and I've written it out here. So to make sense of this expectation, we first sample the Liouville field with insertions alpha z beta x, and then we take the Laplace transform of the quantum area and boundary length. So we just take the exponential of these quantities times mu and mu b. So it's a technical condition that is needed for this to be finite, that the alpha i's and beta j's have to satisfy the so-called Seiberg bounds, but this isn't going to come up in the rest of this talk. Okay, so this quantity here is called the correlation function for the disk, corresponding to these insertions. And when physicists, the object of interest for physicists is these correlation functions. When they say that they want to solve LCFT, they mean they want to compute all of these correlation functions. And this program has been completed at the physics level of rigor. For mathematics, the first instance of such a computation was done by Kupiainen, Rhodes, and Vargas when they computed the 3-point correlation function for the sphere. And they matched the formula in the physics given by Dawn, Otto, Zamolodchikov, and Zamolodchikov, called the VOZZ formula. Remy, and then later Remy Zhu, computed some of these correlation functions for the disk in the case when the bulk cosmological constant mu is equal to 0. So in this expectation, we don't see the quantum area at all. And finally, in very recent work, Guillaume, Kupiainen, Rose, and Vargas computed the 4-point correlation function for the sphere in terms of the 3-point correlation function for the sphere. And this is a special case of what is called the conformal bootstrap. And
can I interrupt and ask a question?
Yeah, of course.
This expression, it depends on mu and mu b.
Yeah.
For which mu's does it? Does it converge?
So, yes. Thanks for the question. That's a good question. So we need at least one of mu and mu b to be positive, and we'll always consider when they're both at least non-negative. So when it's positive, the exponential decay lets you get convergence.
So it always converges when they're both positive.
Yeah, and also when these Seiberg bounds hold.
Under those conditions.
Yeah.
I see.
Yeah. Great. Thanks. Okay. So this conformal bootstrap method apparently lets us compute the endpoint correlation function for the sphere and also for higher genus topologies. And for more on these other works, you can see the excellent talks by Remy and Rhodes at the seminar, which are available on YouTube. Right, okay. So that concludes our brief discussion on the LCFT perspective. Now I'm going to discuss the random planar geometry approach to LQG. So suppose you have a simply connected domain in the field, in the complex plane D, and the function h on D. And we have another simply connected domain D tilde and a conformal map from D to D tilde. We can define a push forward field, which I've written in this way, given by this formula. And it's a function on D tilde. And the reason we define this push forward in this way is that if H tilde is a push forward field of H, then the quantum area and quantum boundary length associated to H tilde are the push forwards of the quantum areas and boundary lengths of H. Okay, so if we consider these quantum areas and boundary lengths as the intrinsic objects of interest, then it's natural to define the notion of a gamma LQG surface or quantum surface. And that's going to be an equivalence class on pairs D comma H, where D comma H is equivalent to D tilde comma H tilde if H and H tilde are related by this push forward relation. Okay. And it's also natural to consider quantum surfaces, which are decorated by some number of marked points. And in this case, you just extend this equivalence relation to have to map the marked points to the corresponding marked points. Okay. Okay, so there's a a particularly important and canonical quantum surface called the quantum disk. And this was introduced by Duplantier, Miller, and Sheffield in the Making of Trees paper. We omit the precise description of QD, but note that a priori it has nothing to do with LCFT. So we're going to write QD for the law of the quantum disk. So the measure QD on the space of quantum surfaces with disk topology is an infinite measure. Okay, quantum disk arises as a scaling limit of random planar maps with a disk topology in the gamma LQG universality class. So as a special case, when gamma is equal to square roots of 8/3, then the quantum disk corresponds to the scaling limit of uniform random planar maps, and which is called the Brownian disk. Okay, so QD gives us a quantum surface with a disk topology and no marked points. If we want a quantum surface with some marked points, here's one natural way to do it. So let M and N be non-negative. We sample a quantum disk from QD, and then we weight by the area to the power of M and the boundary length to the power of N. Then we sample M bulk points from the quantum area measure and N boundary points from the quantum length measure. And this gives us a quantum surface with M plus N marked points. And we write QD Mn for the law of this marked quantum surface. Okay. So let's give a geometric description of the quantum disk via Schramm-Loewner evolution. So suppose you sample a quantum disk conditioned to have boundary length 1, and you independently sample a space-filling SLE curve on this disk. Then the making of trees theorem tells us that the curve decorated quantum surface on the left-hand side here corresponds in some sense to a Brownian excursion in the first quadrant, starting from the boundary point 1 and ending at the vertex 0. So the precise nature of this correspondence is not too important for the rest of this talk. So don't worry if it doesn't make too much sense. So in this diagram on the left, consider the space-filling curve run up until time t. So the region that is covered so far, I have colored in green here. Now, at time t, we define a pair of real numbers, LT and RT, where LT is the quantum length of this red segment, and RT is the quantum length of this blue segment. So at time 0, L0 would be this quantum length of the whole boundary, and R0 would be 0. So that's this boundary point here. And at the end of the exploration procedure, the red and blue lengths are both 0. So that corresponds to the vertex of the cone. So the making of trees theorem states that this pair LT and RT, as time evolves, has the law of Brownian motion with this covariance here, starting at the boundary point 1, 0, ending at the vertex 0, and conditioned to stay inside the first quadrant. Okay, so I want to emphasize that the covariance of this Brownian motion is known modulo this red constant here, a squared, which we call the making of trees variance. Okay, let me give a quick overview of the making of trees theory. So this originates from the seminal work of Duplantier, Miller, and Sheffield. An extensive work in this direction has been done by Gwyn, Holden, Miller, Sheffield, and so on. So one useful thing about the making of trees theorem is that it translates difficult questions on SLE and LQG into hopefully more tractable questions on Brownian motion. And we'll see an example of this later. The making of trees theorem is a continuum counterpart of certain random planar maps, which are decorated by statistical physics models, for which there's a random walk encoding. For instance, when a random planar map is decorated by a uniform spanning tree, one can interpret this random planar map as a making of discrete trees. And the making of trees object described here is a continuum counterpart of that. So as a result, the making of trees theorem is crucial for all proofs of convergence of random planar maps to LQG. Okay. So for more applications and more details on these remarks, You can see the survey of Gwyn, Holden, and Sun. I want to remind that this mating of these variance A squared has been unknown until now. Okay. So that concludes a brief discussion of these two perspectives of quantum disks. And now let's move on to some new research. So these two perspectives give us two different ways of sampling quantum surfaces, which have the disk topology. So the first is this, to sample a quantum surface from QDMN. There's a quantum disk with M marked bulk points and N marked boundary points. The other way is to sample a Liouville field phi with certain bulk and boundary insertions, and then consider the quantum surface which has these bulk and boundary points as marked points. And the beautiful theorem of Cercle is that if you sample phi, a Liouville field with 3 gamma insertions on its boundary, then the quantum surface with these 3 boundary insertions and with the field phi, the law of this quantum surface is a quantum disk with 3 marked boundary points. And there's a multiplicative factor here. So the law is C times the quantum disk law for some constant C. So again, this is possible because we are using the word law in a non-probability sense here. Okay, so the proof of this theorem follows the work of Aru, Huang, and Sun for the sphere case. We're going to give a simpler and perhaps more unified proof of this and similar results, connecting quantum disks to LCFT via what we call uniform embeddings. So, okay, so to that end, it is useful to restate the previous theorem in terms of embeddings. So suppose we sample a quantum surface from QD03. So this is a quantum surface with 3 marked boundary points. If we embed into the disk, sending the 3 marked boundary points to 1 IN minus 1, then the law of the field that arises is going to be the Liouville field with gamma insertions at 1 IN minus 1. So this embedding here is unique because of the Riemann mapping theorem. And now we want to find a variant of this result for the unmarked quantum disk. But one problem that arises is that the unmarked quantum disk has no canonical choice of embedding. So the Riemann mapping theorem let us uniquely choose an embedding here, but that doesn't work when you have no marked points on the boundary. So our approach is we're going to choose an embedding uniformly at random. So what does that mean? We write conf D for the group of conformal automorphisms of the unit disk, and we consider a Haar measure, MD, on this group. And so this is a measure that's invariant under composition with another conformal automorphism. So when we say uniform embedding, we mean to choose a random embedding via the Haar measure. Okay, so I'm going to state this a bit more carefully now. So we call this change of coordinates formula here, which says that if you have a field phi and you have a conformal map G, then we can define a push forward field in the disk, which corresponds to the same quantum surface. So now we define the uniform embedding of a fixed quantum surface, D comma phi naught. To do this embedding, we sample a random function G from the Haar measure, and then we consider the push forward of phi naught under G. So I want to emphasize that even if we start with a fixed choice of quantum surface, we obtain a random field. And this randomness is coming from the choice of embedding.
Can I interrupt again?
Yeah.
I'm still confused. I'm getting very confused because are you sampling from infinite measures again?
Yeah, that's right. This is coming from an infinite measure. That's a good point.
Okay. So I'm confused about what even that means, right? I mean, I think do you have to be?
Right.
Is there no ambiguity here, or is it clear to you what's going on? Because we can't sample from an infinite measure.
Right, that's true. So so when I say sample, I guess let's go all the way back here. So this is maybe the first point when we sample from an infinite measure. I guess one should think of this as in terms of having measures which are not probability measures on certain sample spaces. So we have this measure here, which is P sub D, the product measure of P sub D and this measure on the real line. And so when we say sample H comma C, that's kind of shorthand for considering this infinite measure on this space. Yeah, so it's...
You don't mean sample, you just mean there exists a measure.
Yeah,
and then
I agree.
Mapping is preserving that measure or something like that.
Exactly, that's right. It would be a...
The word sample is just not the right word to be using. I don't know. Maybe you know, since I'm a little bit of a foreigner to this area, I don't want to interrupt if it's a...
No, I completely agree. This is kind of non-standard, but it seems difficult to discuss, to focus on the geometry and the random objects if like I'm carrying like these push forward measures around like all the time. So I agree it's an abuse of notation and it could definitely be confusing, but yeah, hopefully this explanation in terms of measures on sample spaces makes some sense.
Yeah.
Okay.
Yeah, I can also ask a question.
Yeah.
So this Haar measure that is given by, so you have your PSL2 are represented by a hyperbolic disk with a rotation.
Yeah.
Right. So
right.
So this measure is that right? Is correct described by the hyperbolic area measure on the disk times the uniform rotation.
Yeah, that's exactly right.
Is that somehow hint at if we take some semi-classical limit, you should see the hyperbolic disk from your quantum disk? It's probably one example where probably we can already see a first instance where hyperbolic metric pops up naturally from the random.
Right. Okay. So let's. Okay.
Yeah, I don't have to answer right now.
Yeah, this is a very interesting question. I think maybe it'll be a bit clearer, like after a couple of these theorems. Yeah. Okay, so let's get back to that maybe at the end of this talk. Yeah. Okay, so the uniform embedding of a quantum surface is you just choose from Haar measure how you embed this quantum surface. And now we want to consider the uniform embedding of a quantum disk. So we sample a quantum disk from this infinite measure, and we independently sample a map G from the Haar measure. So formally speaking, we're sampling a pair of objects on the space given by the product of quantum surfaces with disk topology and conformal automorphisms. And this gives us an infinite measure on that space. And okay, so consider okay, let's see. Okay, so we sample a quantum disk from QD, and we independently sample a choice of embedding, and this gives us a push forward field. And we write MD times QD for the law of this field. So this object is a random generalized function on the disk. And it comes from there are two sources of randomness that feed into this. The first is a choice of quantum surface, and the second is the choice of embedding. And the theorem that is joined with Nina and Sin is the following. If you take this random field, which comes from the uniform embedding of a quantum disk, then it precisely corresponds to the Liouville field that we defined earlier. And this is up to a multiplicative constant C, which is explicit in terms of the choice of Haar measure. So when you take this random surface and this random embedding, these two sources of randomness combine to give you a very nice Gaussian field in the disk. Okay, so given this result, it's natural to expect similar results for quantum surfaces with marked points. I'll just give a couple of these statements. So consider the Haar measure, MD0, on the space of conformal automorphisms of the disk that fix 0. So this is corresponding to uniformly chosen rotations of the disk. And MD plus minus 1 is a Haar measure on conformal automorphisms of the disk that fix the boundary points 1 and -1. So we can then define a uniform embedding of a quantum disk with one bulk point into the unit disk as follows. We choose any embedding of the quantum disk, which sends the bulk point to 0. Then we apply a random rotation uniformly at random, and this gives us a random field. And this random field has law given by the Liouville field with a gamma insertion at 0. And okay, similarly, if you take a quantum disk with 2 marked boundary points and you embed it in the unit disk, sending those points to 1 and -1, and you perform a Haar measure to choose a random embedding, then the Liouville field, the field that you get is a Liouville field with a gamma insertion at 1 and the gamma insertion at -1. Okay, and given these statements, yeah, one can guess other similar statements. Okay.
All right, the second Haar measure is an infinite measure?
I agree, it's an infinite measure.
Okay.
And this is maybe clearer when you consider, I'll describe this on the infinite strip, the infinite horizontal strip. It corresponds to choosing a random translation of the strip. So if you map the unit disk D plus -1 to the infinite strip with 1 mapped to plus infinity and -1 mapped to minus infinity, then you're choosing a random translation of this disk from Lebesgue measure. And this is actually how we prove the star equation. We map into the horizontal strip, and then we consider the field average process. And the statement then reduces to a Brownian motion identity, which can be checked without too much difficulty. Okay. And then given the star equation, we can prove the other two as well. Okay. Are there any questions on this result?
Sorry, can you remind what are the two 1002? Which one is what?
Oh, sorry, these are just
Okay.
constants which are explicit. So
no, I mean the indices.
oh yes, this is one bulk point. So
One
this is
bulk
a
point.
quantum disk with one bulk point, and we're mapping it into the
Zero.
unit disk with and sending that bulk point to 0. Yeah. Should have maybe included
And
a
0,
picture.
2,
Yeah.
0, 2 means?
It means you have 2 boundary points and no bulk points.
Oh,
so
okay.
the 2 boundary
okay.
points go to plus and minus 1. Yeah.
So for the
These are infinite measure. Sorry.
go ahead.
Those are infinite measure, right?
Yes, that's right. These are already infinite measures. And so this object here is an infinite measure that arises as a product measure of this and this on some product space. And then you take the push forward using this to obtain a measure on the space of distributions on the disk.
Mm-hmm.
So the infinite Haar is also not unique, right? Also
yes,
unique.
that's right. I agree. It's unique up to a certain multiplicative constant. And the choice of that, the Haar measure is going to affect the choice of C10 and C02. And these choices, this is explicit in terms of this. Yet, given the Haar measure, we can recover what constant we get.
Is there some reason you didn't state the C01 result, or?
Oh, yeah.
One boundary point?
So that would still make sense, and you still get the same kind of theorem. Yeah, I guess these are just the ones that arise in this paper. But I completely agree. These related results are all like similarly easy to state. Yeah, so like you'd have the Haar measure on the unit disk of the maps fixing the boundary point 1, say, and you get a Liouville field with 1 insertion at the boundary point 1. Yeah.
Are the proofs all different? I mean, is that why they're not in the paper, or?
Oh, no, the proofs are the same. We proved that they all come from this result by doing some kind of sampling and conditioning type argument. So you just sample another bulk point and you look at how that affects the left-hand side and how that affects the right-hand side. And that gives you these other results. Yeah, they all come from this main theorem. Okay. yeah, the proof starts from this one, and then we prove this one, and then the rest can be deduced. Okay. So maybe I should move on and can answer more questions later. So given this uniform embeddings theorem, we can now compute the making of cheese variance. And I'll be a bit brief here for the sake of time. So we call this unknown constant a squared, which we don't know, and we want to compute it. So the proof is as follows. The making of cheese theorem tells us that if we take a quantum disk conditioned to have boundary length 1, then the expected quantum area is going to be given by this expression here. So this isn't immediately obvious, but this is a Brownian motion fact. It just comes from this description. And that's why the a squared appears in this expression. Now, consider this integration of measures. We take the infinite measure QD on quantum disks, and we can write it as the integral of these QDL measures, where QDL corresponds to quantum disks with boundary length L. So QD1, for instance, corresponds to the quantum disk with boundary length 1, but this is not a probability measure. It's a finite measure, such that when you integrate all of these measures, you get the whole measure QD. So this is in some sense restricting to the event that you have boundary length equal to 1. Okay, so now we want to compute this expected quantum area of the quantum disk conditioned to have boundary length 1 in a different way. So the quantum disk with boundary length 1 is this QD1. Since we're conditioning to have unit boundary length, we need to divide by the total size of this measure. And we're taking the expected value of this area. Now, QD10 is a quantum disk with 1 marked bulk point, and is obtained from QD by area weighting and sampling a bulk point. So as a result, this area weighting here can be translated to this total size of the measure QD101. So, okay, the point is that we now have 2 different ways of computing the same quantity. On the top equation, we don't know the value of a squared. And on the bottom equation, we can use LCFT to compute these 2 quantities. And the way to do this is as follows. So very briefly, the uniform embedding theorem tells you that the quantum disk with 1 marked bulk point can be understood in terms of the Liouville field with 1 insertion at the origin. And there's an explicit constant of proportionality. Work of Guillaume on the Theodorov-Borchardt formula then lets you compute the boundary length law of this Liouville field. And so now you can directly compare the quantum disk with boundary length L to the Liouville fields with boundary length L, and you get this identity here. So in this way, we can compute the size of QD10L. Okay, so the LCFT input is telling us the law of the boundary length of this field. And a similar argument using LCFT input from Guillaume and Tunan will let you compute the other quantity, the size of the measure of quantum disks with boundary length L. So we know this quantity and this quantity using LCFT. These are completely explicit formulas. This is a known value. And so you can plug them in here to recover the value of a squared. And that gives you the making of cheese variance. Okay. Okay, now in the time I have left, I want to briefly explain the proof sketch of the FZZ formula. So what is the FZZ formula? It's a formula proposed by Fateev, Zamolodchikov and Zamolodchikov in the physics literature for the correlation function corresponding to 1 insertion in the disk. And so that's this quantity here. Let's recall what this means. So this correlation function is defined for mu and mu b positive by sampling a Liouville field phi from this infinite measure here with an alpha insertion at 0, and then taking the Laplace transform of the quantum area and boundary length. Now, note that in our previous definition, we didn't have this -1 here. And this -1 is necessary here to make this integral converge. This is because the insertions don't satisfy the the Seiberg bounds. So we need to do some kind of truncation to make this integral a finite quantity. Okay, so this 1-point correlation function for the disk has, in joint work with Guillaume and Sin, we computed explicitly, and it's this quantity here. And the relationship between mu and mu beta, sorry, mu and mu b, and this quantity is via this parameter s, which is defined in this kind of complicated way in terms of this inverse cosine. Yeah. So this seems kind of intractable, but we'll see how this is workable. Okay, so why is FZZ important? Well, the conformal bootstrap program reduces the computation of correlation functions to the irreducible correlation functions called structure constants. So this is a kind of recursive approach, like how the 4-point quantum sphere, the 4-point sphere correlation function can be reduced to the 3-point function. And for surfaces without boundary, the only structure constant that we need is the DOZZ formula. That's a 3-point function for the sphere. Now, if you consider instead surfaces with boundary and you want to do this recursive reducing procedure, then the FZZ formula is one of the structure constants. And the remaining cases are when you have one bulk and one boundary insertion, or when you have 3 boundary insertions. And this is joint work with Guillaume, Xin, and Tunan, and this is in progress. And it depends on the FZZ formula. So this is necessary to solve the LCFT. Okay, the second application of this formula is in the integrability of the conformal loop ensemble. And this is joint with Xin, and I'll explain a bit about this in the last slide if there's time. Okay, so the FZZ formula was kind of really complicated, but at the end of the day, it's the Laplace transform of the quantum area and boundary length of the Liouville field. And so it describes the joint law of the quantum area and boundary length. Now, Guillaume has already computed the boundary length law of the Liouville field with one insertion at the origin. And so that allows us to reduce the FZZ formula to this somewhat more appealing statement, which is as follows. So if alpha is a parameter between gamma over 2 and q, if we sample a Liouville field with alpha insertion at the origin, phi, and we condition on having boundary length equal to 1, then the law of the quantum area is going to be this inverse gamma distribution here, where the parameters a and b of this distribution are explicit in terms of alpha and gamma. Okay, so we understand the conditional law of the quantum area given the quantum boundary length of the Liouville field. Okay, so the proof of this uses tools from random conformal geometry, namely the quantum zipper and the mating of trees theorem. So the quantum zipper refers to this phenomenon where if you have a quantum surface of a certain type and you sample an independent SLE type curve on top of this quantum surface and you cut along this curve, then you get 2 independent quantum surfaces. This is not a statement that's true in full generality, of course. It depends, you have to choose the quantum surface and SLE appropriately. The first instance of this was done by Sheffield, and then later on in the mating of trees paper again. So previous proofs of the DOZZ formula use conformal field theory methods, namely the BPZ equation and operator product expansion. So these techniques we're using are kind of novel in this setting. Okay, so the 2 inputs we need are as follows. We need a mating of trees input, which tells us that a certain object called a weight gamma squared over 2 quantum disk corresponds to a Brownian excursion in the cone. So just from the previous pictures, like a correspondence of this type should not be surprising. And the other input we need is a certain quantum zipper input, where on the left-hand side, we have a Liouville field with alpha insertion at 0 and boundary length 1. We draw a curve on it and we cut along that curve. And this produces another field, which is a Liouville field with alpha insertion at 0 and a random boundary length. Okay, so I'm going to say a bit more about these. So this weight gamma squared over 2 quantum disk was introduced by Duplantier, Miller, and Sheffield. And the main result we need about these objects is that when you have such a quantum disk, you can relate it to a Brownian excursion in the cone in this way. If the left boundary length is L and the right boundary length is R, then this object corresponds to a Brownian excursion in the cone from L, 0 to R, to 0, R. And the green area, the quantum area of this disk, is exactly the duration of the Brownian motion. So that's the first input we need. And the proof is via mating of trees. And it essentially arises when you take the mating of trees theorem for the disk, and you look at the space filling curve and stop it at a certain stopping time, then this region on the left is one of these quantum disks. And this region on the right is going to be this, this Brownian motion. So this isn't supposed to make sense, but it's just supposed to convey like an idea of how this might be done. Okay, so you have a mating of trees input. And we also have a recursive quantum zipper. I'll spend a bit more time on this one. So the statement is as follows. On the left-hand side, you sample a Liouville field with alpha insertion at 0 and boundary length equal to 1. And independently, you sample a certain SLE kappa type curve, which is a loop here. So we sample these two things independently, and then we cut along this blue curve. And this gives us two quantum surfaces. The left quantum surface is precisely the object that we just discussed. And the right quantum surface is going to be a Liouville field with alpha insertion at 0. And these two objects are conditionally independent given the quantum length in blue. So if I tell you the interface length here and I cut, then I get two objects which are conditionally independent. Okay, so how does this help? The point is that this is a recursive relation because on the left we have a Liouville field and on the right we have the same Liouville field, possibly with a different boundary length. And so this lets us obtain a distributional identity for the area of the quantum disk here. So let X be the quantum area on the left. So that's a green plus a gray region. Now, the one nice property about the Liouville field is a certain scaling property. If I have a Liouville field with boundary length 1, then the law of the quantum area, and I want to rescale it to have boundary length R, then I should rescale this quantum area by R squared. And so as a result, if we let A be the quantum area of this disk, and then we can write X, that's the total quantum area, is equal to A plus R squared X tilde, where X tilde is an independent copy of X. So again, this R squared factor here is coming from a scaling relation between this disk and this disk. Okay. And so the claim is that this is enough to prove that X has an inverse gamma distribution. To do so, the approach is to use Brownian motion. So we obtain a distributional identity for Brownian motion. You consider a cone in the plane. You start Brownian motion at 1 and run it and condition it to exit the cone at 0. Consider the time when it hits this ray here, and let R be this length, let A be the duration of this green segment, and T the duration of this gray segment. Now, if you let Y be the total duration of this Brownian motion, then we have Y is equal to A plus T, just by definition. And it's a Brownian motion fact that if you condition on R, then the law of T is precisely that of R squared Y. And this shouldn't be, this is not obvious, but it should be plausible because when you rescale Brownian motion by a factor of R, then the duration should scale like a factor of R squared. This is Brownian scaling. And so this gives us a distributional identity for the inverse gamma distribution. And this, you'll see that this is the same identity that we had earlier. Okay. And consequently, if we can sample independent A1, R1, A2, R2, and so on and so forth, and because Y satisfies this recursive identity, so we can just iterate it infinitely many times to obtain that Y agrees in law with this infinite sum here. And you can do the same thing for X, and you get this infinite sum. And these are clearly the same sum. So we conclude that X and Y agree in law. And it's a Brownian motion. Okay, X is the quantum area of the quantum disk. and y is the duration of this Brownian motion. And it's a Brownian motion fact that this duration has the inverse gamma distribution. And so X has an inverse gamma distribution that we wanted. Okay. Right. And the law of Y depends on the variance of this Brownian motion. So to determine the parameters for this inverse gamma distribution, we do need the mating of trees variance A squared. Okay. So there's a proof sketch for this quantum zipper, which is essentially a very geometric kind of argument, where you start with an infinite version given by the Plantin-Miller-Sheffield, pinch it to get a finite version, sample a bulk point, and then pinch this red length to 0, and then do some reweighting. This isn't meant to make sense. It's just kind of a high-level overview of the, like, hey, we're doing geometry, right? Okay, great. So the summary of this talk is that there are two sources of integrability in Liouville quantum gravity, one coming from the correlation functions of LCFT. And for instance, these are the structure constants like the DOZZ formula and FZZ formula, and we can get higher order ones using the conformal bootstrap. The other source of integrability is from mating of trees. And here we can use Brownian motion identities. And there's a third source of integrability in conformal probability coming from SLE. So for instance, the Cardi formula for crossing probabilities of percolation, the Schramm formula for right crossing probability of SLE, and so on and so forth. It's a joint project with SYN to blend these three sources of integrability to give new results in each direction. Okay, so I have two more slides, but I'll just show the pictures and we can call it a day. So this first slide says, this is joined with Nina and SYN. And if you sample an SLE kappa rho curve in the upper half plane from 0 to infinity, and you consider this mapping out function psi, then we understand exactly the moments of psi prime of 1. And it's kind of this big, difficult formula here, which involves a double gamma function, which arises in, for instance, the DOZZ formula. So this formula here makes it probably difficult to compute this quantity via Ito calculus, but maybe it's doable. I don't know. Okay. And for the second result, it's got to do with CLE in the plane. If you fix 3 points, Z1, Z2, and Z3, sample a CLE on the plane, and then look at the outermost loops around these points that do not contain the other points, then we have a joint moment result for the conformal radii of the red point to the red curve, blue point to the blue curve, and purple point to the purple curve. And this exact formula is supposed, we have an exact formula for this quantity, and it's corresponding to the imaginary DOZZ formula, according to the physicists, Eclair, Jacobson, Salia. And we also have a 2-point version of this, which verifies the Kenyon-Wilson formula for CLE on the sphere. Yeah. Yeah, I'm definitely happy to stay and chat more about this stuff, but I think that's the end of my time. I think I even went a bit over. So thanks for your patience.
Thank you very much, Maurice.